Welcome dear student, welcome to my channel Talking Physics with Piyas Sarkar. So today we learn about application of Gauss law. If I asked you that what is the electric field of a cube, if a charge q is placed at the center of a cube, then what is the total flux, and if the charge is kept at one of its vertex, here is charge q is placed, then what is the total flux and what is the flux in each surface? What is the total flux of the cube and what is the flux of each surface or each faces? As we know that there are 6 faces of a cube. So today lecture we can first know the application of Gauss's law and then we go with some numericals like this. Okay, let's start. So who are not aware of Gauss's law, please go to my channel and type Gauss law, which it states that the total electric field around any closed surface must be equal to total charge divided by permittivity of free space if the charge is placed in free space. So this is the Gauss law and this is the very important to find the electric field at any point from a charge body. Okay, so now we can go with we can find out the electric field due to a infinitely charged wire. So we can go with the electric field E field of infinitely charged wire. Let us take an infinitely charged wire. For convenience we can say that this is positively charged. So we have to find out the electric field at point P, which is at a distance r from this small r. So to find the electric field at a distance from the wire, we can first draw a surface which is known as Gaussian surface. Gaussian surface, the properties of Gaussian surface is it must be passes through the point. It must be passes through this point, and the electric field, as this is positive charge, from symmetry the electric field is outside the charge. So this field is the Gaussian surface is passed through the point P, and electric field has same magnitude all over the surface. That is, the Gaussian surface must have symmetry about this point, otherwise this not be a Gaussian surface. So for convenient, if we draw a cone, a cylindrical Gaussian surface in this region passing through this point P obviously, so we can get this is the Gaussian surface. This surface, it is known as cylindrical Gaussian surface. Cylindrical Gaussian surface, because at every point is surface the value of E has constant, magnitude of E is constant. So it has 3 faces, number 1, number 2, number 3. Among these 2 faces are symmetrical or equal. Now if we say that a very small element of phase 1, that is ds1, and very small element in the n phase ds3, so it has 3 faces total. 2 are the flat n faces and 1 is curved faces. And here also we can find out a small surface, say ds3 or ds3 or ds2. Now as we know that if we take a closed surface S and take a very small elementary surface ds, then the vector, area vector, it must be perpendicular to this surface. This is the direction of ds. So in this way, in this case, the area vector of ds1 must be radially outward and perpendicular to the plane. And for similarly for ds3, the area vector direction of area vector is along this direction, which is makes in the two faces E makes 90-degree angle. So here we, as we know, EDS cos 90, that is 0. So for phase 1 and in phase 3, the total flux, if we say is this phi, the total flux is 0. So we can only consider the flux for the GS2. Now we know that the Gauss's law is integration E ds equal to total charge is q by epsilon naught. Okay. So for this infinite way, we can consider lambda is the linear charge density, that is charge by length. If the length is L of this wire, for convenience we can find out the length of the wire is L, that is it is not infinite, it is finite. So in this case lambda equal to q by L. So q equal to L lambda. Therefore as E has constant, it is taken outside the integral, E integration ds must be q, that is lambda L by epsilon naught. So E integration ds lambda L by epsilon naught. Therefore ds is the area of the curved surface, that is if the radius is if the radius of this cylinder is r, then we can say that E multiplied by 2 pi rl is equal to lambda L divided by epsilon naught. L must be cancelled out, so we can get the electric field at a point P is E equal to lambda divided by twice pi r epsilon naught. Lambda 2 pi r epsilon naught, and in vector notation it is written as lambda by 2 pi r epsilon naught into n cap, where n cap is the unit vector perpendicular to the line charge density or wire. So this is the formula of electric field due to an infinite wire. So in this case we can find out the electric field with the help of Gauss theorem. Okay. Next we go with infinite sheet. Next we go with infinite sheet to form out the electric field. Infinite sheet means the sheet which is the infinite sheet is the sheet which is very large in their size with respect to its dimension. Let us take, so next point is electric field due to infinite sheet. Okay. So as we take, suppose this is a infinite sheet with positive charge. We have to find out again the electric field at a point P. So suppose the point P is at a distance r from the sheet. By symmetry, the electric field is radially outward due to positive charge, and if we take another point P dash due to symmetry, again here the electric field is outside from the positive charge. So at first we have to consider the Gaussian surface. Here we can draw the Gaussian surface like this, which is passes through the point P, this type of Gaussian surface which is cylindrical in shape. So again here there are three faces. Okay, here face S1, this is the curved face, this is S2, this face, and also this face is S3. So this is just the reverse of the previous case. Here if we consider this a small element, that is ds3, then ds3 must be parallel to vector E. And here also the ds3 is along E, because as E is perpendicular to the surface S3 and E is perpendicular to surface S1, so E and ds3 must be parallel to each other. Therefore, and this curved surface, due to this curved surface, E is passing through this direction and this is ds2. So the angle is 90 degrees, so this is cancelled out. So we can get E ds equal to q by epsilon naught. But here, as this is a sheet, so here we can get a surface charge density sigma equal to q by total charge divided by area. Area A is the area of the sheet. A is the total area of the sheet. So you can write as q equal to sigma into A. Sigma is surface charge density. So you can write it as sigma A by epsilon naught. Now here we consider two similar surfaces, S1 and S3. So E integration ds means A, the total area. And here this area is A, therefore 2A, E into 2A equal to sigma A divided by epsilon naught. Therefore A B cancel, therefore E must be equal to sigma divided by twice epsilon naught. In vector notation it is given by sigma divided by 2 epsilon naught n cap. Okay, E equal to sigma by 2 epsilon naught n cap. Here we can consider that E is independent of R, that is, it is independent of position of the point. And also this is the infinite sheet does not exist in practical. Okay, if for in practical, in real, the charge is considered to be midpoint of the sheet. The charge is considered to be midpoint of the sheet. That is, the charge in the edge of the sheet is considered to be 0. And also here the dimension of the sheet must be much greater than to the distance. That is, the point P is very small. The distance of sheet and P, that is the R, is much small than the size of the sheet. So it is called as infinite sheet. Suppose a little ant is moving in a large sheet, or if it is moving in a sheet like this wall, so this is to the end, this is considered to be infinite. So in this case equal to 2 sigma by 2 epsilon naught into n cap. Okay, so now we go with some numericals of Gauss law. So we can go with some cube problem. Suppose a charge is placed at the center of a charge q is placed at the center of a cube, then what is the flux, total flux of the cube? The total flux phi total equal to total charge divided by epsilon naught. Now this charge or this flux is divided between 6 phases. So flux in each phases, if we say phi each, equal to q divided by 6 epsilon naught. This is very simple case of square. Now we go with, if this charge is placed in one of its vertex or corner, then what will be the total flux? Suppose a charge plus q is placed at this point, one of its vertex. So according to Gauss law is applicable when the charge is kept in a closed surface. For an unclosed surface, this law is invalid. If we put a charge in a vertex, then it does not means a closed surface. So it can be proved that there are 8 cube required to be formed a closed surface. Therefore, for 8 cube, the total flux phi total must be equal to total charge divided by epsilon naught. So for 1 cube, it must be equal to q by 8 epsilon naught. Okay. So for 1 cube, it is equal to 8 q by epsilon naught. Now, if it is asked that what is the flux due to each phases, here we cannot write that 1 cube means 6 phase, that is the total flux through each phase is q by 6 into 8 epsilon, that is 48 epsilon 0. This is very, very important for JEE or NET exam. Here only the flux through 3 phases is considered, because the other 3 phase which meets at this corner, which phase? This phase, this upper phase and this phase meet at this point. So here the total flux is 0. For these 3 flux is 0, because here E and ds are perpendicular to each other. So the flux contributes due to only remaining 3 phases. So 1 cube equal to q by 8 epsilon 0. We can write that for 3 phases it is equal to q by 8 epsilon naught. So for one phase it is 1 by 3 into q by 8 epsilon naught, that is q by 24 epsilon naught. This type of concept or question is asked in your previous exam or in joint entrance exam. Very, very important. Okay. Next we go with a similar concept of infinite wire. Suppose 2 infinite wire is kept parallel to each other. Then if we divided it in region 1, region 2 and region 3, then what will be the net electric field? Here we say that in right side the electric field is, sorry, this is not infinite wire, this is a sheet, plain sheet. If you consider this a plain sheet, it is considered to be a sheet. So for electric field on the right side it is taken as positive, and electric field in the left side it is taken as negative. Now as this is positively charged, so here the direction of electric field due to number 1 sheet is E1 is along left side, and direction of electric field due to sheet 2, this is sheet 1 and this is sheet 2, due to this sheet 2 is also in left side. So the total electric field E becomes E1 plus E2. This is considered to be region 1. We know that E equal to sigma upon twice epsilon naught, but as it is in left side, so the direction is minus sigma upon 2 epsilon naught minus sigma by 2 epsilon naught, that is sigma by epsilon naught with negative sign. Okay. So this is in region 1. In region 2, the electric field due to sheet 1 is along this direction, because due to positive charge the electric field is outside the sheet, and for sheet 2 this is along this direction in region 2. as the two sheets are symmetrical, therefore total electric field is 0 in the medial region, because they are same direction but opposite in they are same magnitude but opposite in direction. In region 3, due to this sheet E1 equal to sigma by 2 epsilon naught, it is away from the sheet, and due to this the electric field E2 is also away from the sheet, sigma upon 2 epsilon naught. Therefore in region, this is region 1, this is in region 2, and then region 3, total electric field E becomes E1 plus E2, that is sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, which is given sigma by epsilon naught. Magnitude is same but opposite in direction. Okay, so I hope you all understand. In next day we will go with some more example, spherically symmetric ball or sphere and the application of Gauss law. If you like my channel, subscribe and view more and much. Thank you for today. Thank you.